Hello, everyone. Good morning or good afternoon, depending where you are. Let's start now the second day of CASSW Rio Grande do Sul workshop. Today, we are going to have 2 talks in the morning and more 2 talks after the lunchtime. Finally, from 4 p.m., we also will have 2 poster sessions. Don't forget to put your name and institution on YouTube chat, and fill the form that will be available soon. Once again, I would like to thank the presence of all the speakers and the participants. Now I would like to invite Professor Matheus Grellert from UFSC to present the first speaker.
Thank you, Alexandra. Hello, everyone. Good morning. My name is Matheus. I'm a professor at the Federal University of Santa Catarina. Nice to meet you all. Nice to see some familiar faces also in the YouTube discussions yesterday and today as well. I'm here to proudly present Felipe França. He's giving us a very interesting talk about weightless neural networks. For us hardware designers, this is very important because the weights are one of the most, main culprits in energy consumption in these networks, in circuits for neural networks. So Felipe França is an electronics engineer from the Federal University of Rio de Janeiro. He's also a master's in computer science at the same university. And he also has a PhD in neurosystems engineering at from the Imperial College of Science, Technology and Medicine in the UK, if I'm not mistaken. He's currently an invited professor at the Systems Engineering and Computer Science program, the copy of the Federal University of Rio de Janeiro. He has a very large set of publications in the fields of neuro-artificial networks. He has over 200 scientific papers and 2 granted patents. One who is very interesting, which is about the talk today of weightless neural networks. I've read it, and it's a very good paper. Congratulations, Felipe. And he also has experience in computer science and electronics engineering. He's currently working with artificial neural networks, weightless neural networks, computer architecture, asynchronous digital circuits, cryptographic circuits, data flow computing, distributed algorithms, collective robotics, and intelligent transportation systems. That's a very wide curriculum. Congratulations. So Felipe, without further ado, you can begin. Thank you very much.
Thank you, Matheus, for the very nice introduction. Let me share my presentation here. First, I'd like to thank my former PhD supervisor, Igor Alexander, who was the one that I used this expression, look, man, no weights. It was a long time ago. I couldn't resist to repeat it here. It's a long time forgotten. Well, let's start with what everybody knows about artificial neural networks. We use this McCullogh and Pitts neural model from the 50s. Everybody knows and everybody uses it. Works like that. You have a sum of weighted inputs, and you go through an activation function, and you decide your result. And here below you see a photo of a real neuron. And apart from, let me use my laser pen here. Okay, hold on. It's not working. Laser pen. I don't know. Are you seeing my laser pen or not? I can't see it. Laser blue. Well, anyway, This part here, in green, is the dendritic tree of a neuron, and that's the most noticeable morphological part of the neuron. The weightless neural model, you can imagine that has this biological plausibility appeal from this dendritic tree. The dendritic tree works like a decoder of many inputs coming from other neurons. And in fact, Christopher Koch some time ago explicit this kind of computation called analog vector operation, when you have a set of inhibitory and excitatory neurons giving input to the dendritic tree of this post-synaptic neuron. And depending where a positive or a neutral, negative input at the dendritic tree, and depend on the height of the dendritic tree, you have a result. Please notice this inhibitory neuron I7 here in the middle, more or less. It will shunt an excitation that would come from below, and this would not make any effect from at the neuron's response. Only the other small branch was responsible for producing the output. In this case, was on. Okay, and I don't know. I didn't decide if this neuron is excitatory or inhibitory, but it was, the output was okay, fire. The weightless neural model, it's not new. It's from 59. Bledsoe and Browning used this n-tuple classifier. And at that time, we didn't have Google Scholar and stuff like that, but there were parallel research going on in the UK, and Igor Alexander was already working on this kind of approach, and he described it as a universal logic circuit. It was a memory, and in fact, it is. So how the weightless neuron is implemented? Well, we can see a run node implementing a neuron function. Imagine that the inputs of this neuron 0, 1, and the input will be decoded, and will be stored as one. When the first question, it appears how this can generalize a response. If I see the exact same thing, okay, but if not, okay, we want to recognize patterns and similar patterns. So now I start presenting you the wizard. It's from Wilk, Stohan, and Alexander recognition device, this acronym. And it works like that. You have this input retina, and you have a set of these neurons. Well, the input retina is mapped, gives input in a pseudo-random way, to all of these input addresses of these runs that are initially cleared with zeros, okay? So let's train this set of runs that we'll call discriminator. And we want this discriminator to recognize letter ages, okay? So how it works? In a binary implementation, or in a binary setting, we have the dark in the input retina will be ones, and the clear ones will be zeros. So I produce different addresses, and at that, the content addressed will be increased, okay? That's it. So if I present the same letter age in the classification phase, all the inputs, all the contents will be one as well. But I would like to train all the other ages, different ages, and if I do that, I will have different contents on the runs, okay, on the set of runs. Well, let's see how you do that. We use for this before going to the final response, I will check through this threshold, and that's the original setup for wizard. If it's 0, well, it goes 0 like that. If it's not, it will be 1. So trees will be 1. But let's go for a classification phase and present a non-age pattern, okay? It's not very much like an age, so it should be rejected. So let's see what will happen here. Well, we have produced these addresses, and you see that if I use this threshold a little bit higher, the response will be 2. Okay, it's not so good, so it should be not an age. And that's how it works. We use this content, increasing contents on brands from the 2009 and 2010, because the applications meant to use wizard were not able to cope with big data, with a large data set. So many cases you have to be very careful with the training of weightless neural network. That's why perhaps it was not very popular for some time. And so with this simple use of this threshold, or I think it was misused before, you could deal with any size, practically any data size. We have this published some time ago, and the interesting stuff about these contents that they can increase at each memory content in a multi-discriminator systems. I mean, imagine a wizard architecture that would like to recognize digits from 0 to 9, and I have this input. So I present this input. Well, for us it's clear that's 1, but the wizard needs to discriminate it, and so each set of runs is dedicated to one of the digits, and you present the input pattern to all of them. So you have responses from all of them, and that's how you decide what was the response. In this case, it was a 1. This is a kind of real setup where you can see the 1 is similar, kind of similar to 7, and 7 was the second response to that. But you could see in the title before that we could produce mental images, okay, and that is because in this system it's very easy to ask for a discriminator what you have learned. Give me an example of that, because the contents are there. So you just should go in the other direction and produce, and using different thresholds perhaps, and you could see what each discriminator has learned if you are in doubt. Okay. Well, wizard is now it's kind of starting to get very good attention, and we have defined and produced the precise VC dimension for the model, which is huge, and at the same time, what is interesting, it can generalize quite well. I prefer here to present the many applications of and the results of wizard, and I have to talk first. In the beginning, wizard was a machine. I couldn't. Unfortunately, I don't have any photo of it, but it was a patent hardware from Alexander and his group, and it was firstly used in robotic vision. At robotic arms use the input from a camera, and it could pick objects in a conveyor belt passing through. It was also applied in banknotes, high-speed banknote counters. Okay. More close to us, Brazilians, we have this. That's for old guys like me. Okay. In the beginning, the Fantastical program from Global produced the avatar called EvaByte, a virtual reporter that learned. It was an avatar for this actress in the right, and the focus on the reporter was on her talking. The animation, the 3D animation, has to talk a lot of stuff, and we humans are very sensitive to the lip sync. So if you do an animation, the lip sync, for pay attention on your face. The lip sync should be perfect, otherwise you feel something odd. Okay, and that actress, it was the chosen one for producing the voice of the Eva, and it worked with. Like that, the system had two wizards, one looking for where is the actress mouth, and the other classifying what kind of keyframe, what kind of pattern the mouth was doing. And that this was used to accelerate the production of the 3D animation. The time was reduced for kind of 1 week to some hours. At that time, it was a good thing. Today we have this online, and we using other models, and we could do that as well if you want. Another result was in the recognition of HIV many viruses, and including drug-resistant subtypes. We have results on early detection of epileptic seizures with the colleagues in Coimbra, Portugal, and other EEG application. And that was the result. The best results were produced by Wizard compared with the other known models like SVM. This one was another application that we produced in a project at the Federal University of Rio and colleagues. And the idea is to produce an IPS, an indoor positioning system based on Wizard, in a way that let's use Wizard to learn a pattern of Wi-Fi radiations using the MAC address, the signal strength, noise, and if you could associate each location to a different signature. And so that's why we did this IPS that works. In fact, I will just show here a very quick video, but I'll not show everything. But we did this system in a whole, and it's not being used until now, because I'm going to use it in an app for FRJ security when we go back from the pandemics. And the idea, we have the GPS information, and we also have, if you have the plans of a building, you can get, in this case, when we were in the second floor of this building. And this was a small demo we did for FINAP. It was the sponsor of this project. And just show a bit of it, it's already too long. It was not a big, we just learned some few points, not lots of points, and that for having very good precision, 1 meter precision, we should train it more, but that was the beginning of it. Okay, he's in the corridor now and he's going. Okay, that's it. We have here another application that was credit assignment. We have a publication on that. And this paper was good because we have to exercise Wizard, in this case, CASSW-Wizard. That's a clustering version of Wizard that I do not have time to explain, but it deals with the dynamic creation of discriminator, that set of randoms. And the interesting thing here is to show that the orders of magnitude faster this model can be, because you could think of using the normal, the McCullogh-Pitts neuron. Every time you work with it, you're doing a simulation of a neural network, while in our weightless neural network, the semantic gap is much shorter, okay? And so you could see that as the amount of time and size of data size, you get orders of magnitude faster, mainly in training. And we got reasonable good results with that. In this credit assignment, it was also a competition where we got good places in both tasks of and all the other competitors were from economics, and we were not. In fact, I'm very bad at economics. Another result is on that's using the clustering CASSW-Wizard, and what's in data string clustering, that in situations you have to cluster dynamically lots of data points. You have this problem in networking and high-speed trading and other stuff. And here is it's the result of a data set. In fact, the complex 8 is kind of a very good name for it, and it's a challenge, and we got very good results with the CASSW-Wizard. We even applied it to play rock, paper, scissors, and in ontology and alignment. We have also results in computational linguistics with Hugo Carneiro, that was our PhD student. Priscilla is a collaborator, and we'll cite her later, and we supervised Hugo. He got very, very good results, and in the computational linguistics, in this case, it was a tagger, and we got that time, it was 2015. We are very good against Petrov et al. That was Google's, in fact, tagger, so we were very okay with that. And in fact, the Turkish, that's the last line, I think nobody has this kind of result anywhere until now. I think the last time I checked, there was not. Afterwards, we could devise a universal multilingual tagger, and that we would not need any special setup according to the language. And we compared with many other taggers that was including ones based on LSTM, that's a known deep neural network. And we got competitive with it. We're not beating most of them, but we are okay, and we do it with training much, much faster than all of them. And Marmot is the MM, I think, is the best, is the state of art at the moment. It still is. Well, I will present you also this object tracker based on Wizard. The idea is, the problem is, follow an object identified in the first frame. Also, the tracker doesn't know what to track, and they will teach you, for instance, like that. In the first frame, you do that and go looking for it. Go, where are you, Sylvester? And you have to follow Sylvester independent of the luminosity and the position, etc. Here's a more challenge problem with the tiger. And these two videos are benchmark videos, okay? And we are using a tracker based on Wizard. And how we do that? Well, we work with this queue of discriminators, and you start locking on what you want to follow, okay? And the discriminator one is trained to, oh, this is the tiger. So next frame, I look around that for looking for the tiger. That's just, it's not so big like that, but just to illustrate, okay? And for instance, in this case, 85% of the runs were activated. Okay, I keep looking for, this is still the tiger. And imagine that the tiger get to this position. So this is very different from the tiger I knew before. So what I do, I will train another one that was the best tiger looking around. So I should be the tiger, but it's different now. So I learn it and assumes tracking. So I keep looking. When it happens again, to change the aspect, if it's okay, I look, it got back to the first discriminator. It's much more similar to the first one than the second one. So I go back to there. If it's very, very different for the other ones, I create another one. And that's very simple, and it works very, very well. Here we have let me show you the multi-object tracker, because I can, why not follow many stuff and arbitrary stuff. So Daniel Nunes, sorry, that guy in front was the one. I am there on the right. Priscila Lima is on the left, and Diego Souza is up there. I was not the challenging one. Priscilla, of course, is, because she made lots of different, completely different patterns going on. And I was just amazed. Oh, it worked very well. And okay. All right. So very recently, we use this. We exercised this object tracking in a very interesting system, and the problem, in fact, is the case of computational storage devices. And the problem was the same. Let's have lots of a big benchmark on video frames, and let's track. The problem was to get the tracking of the objects that were defined. In a conventional system, you have a conventional, the videos are stored in flash SSDs, and the host, the CPU, you have to process the whole video. In a computational storage system, the drives itself, they are able to process the videos in many ways, and the host also participates merging results, for instance, okay? It's a system like that. In fact, each of these drives is a computational drive system, a computational storage drive, and it has a ARM53 as for applications, just to run applications. It has other ARMs, but other processors to do other stuff for controlling the access to the NAND runs, etc. But it has in situ processing. And in this paper, we compared our wizard with other known object trackers, and you can see that the results for wizard are the closest one to the best point, that is the right below, very near to the half on the x-axis, because the y-axis is energy consumption and the accuracy is in that one. So we got very well. We didn't get the best accuracy, neither the best energy, but we got the best combination of both. Okay, another application is on the production of PUFS, physically unclonable functions. And the idea was to use, to think of with in hardware where the memory would, using the setup, the reset, the contents that would appear randomly in the RAMs as a signature to produce a PUF. There are many, from this basic architecture here, there was lots of variations, and we measured them, and we got, the best one is in the bottom, where you got near half, means 50%, it's a coin, very near half. The lower this number is, the percentage of accuracy from a machine learning attack. In this case, you have 3 ones: gradient boost, SVM, and I think linear regression. I don't know, probably. We got these very nice results. If you use this variation that I can't recall now what's the right one, because we do the rotations, and also there was a filter outside the wizard. We did very well with this. Okay, we also have this extension for working with regression, and the idea is to include a dimension in the contents of the runs, where you could store the values, okay, from where from the observation you are doing, you are processing. And in this problem, we do also ensemble of regressors, and we got also very good results. I'm presenting this because this is our kind of recent results, and just to show how acceptable are these results. Hold on, where it? I have something there. Well, I was kind of short, but I'm okay with that. I could present. We are doing some work now on using weightless neural networks inside hardware systems, in this case on the SSD controller, to dynamically set the voltage for polarizing the NAND memories, in order to give them longer life and quick and less errors to process. This is ongoing work. We are working also on new training algorithms in reinforcement learning. Next week we are going to present some nice results at the European Symposium on Artificial Neural Networks. We are also working on deep neural network training acceleration. We have already got results on that, and there are other stuff going on. Well, I'd like to cite here many colleagues that work with the weightless neural networks. Priscilla Lima, my partner, and others like my ex-supervisor that I work with, Ellie Morton, Massimo De Gregori in Italy, Sandeep Kundu in the PUF, João Gama in the data stream clustering, Paulo Carvalho in Coimbra in the AEG, also Carlos César Teixeira, Pedreira, my colleague there, Vladimir Alves from NGD Systems, Maurício Breternitz in the Bloom filter implementation of Wizard, because when you use high dimensional spaces, that means when you use very large runs, you cannot think of implementing the whole space. You should deal with in another way. So it was nice to have Mauricio on board on this. We also have many ex-students that are now colleagues or working elsewhere, either in Brazil or outside, and in other places, Okay, if anyone gets interested on testing using Wizard, you can go. That's the time of having a snapshot of the screen, because it is at this site you get the Wizard package. You can do a lot of stuff, and please use this command to get the latest version, because otherwise I think it goes for the first version, something like that, because most of the guys that produce this package are now other places, and the update goes slowly now. Well, I think I'm done. Thank you very much.
Thank you very much, Felipe, for this very interesting talk. I had no idea that you could easily implement it in so many different applications. It's very interesting to see how you can use weightless neural networks for all types of systems and applications. Very nice. I'm also very overwhelmed with the speed in which it is trained. I think that since we don't have so far any questions from the audience, so guys, don't be shy. You can make any questions that you'd like for Professor Felipe. I have a question about the training process, because in this case, it doesn't seem like gradient descent applies. So how do you do training? Because I think you have several different variables, as in the number of REM units. I think it's probably one unknown variable that you have to figure out the best number of REM units and stuff like that. So how's the training process occurs?
Okay, good question, Matheus. That depends very much on the input. The problem or the delicate point of using weightless neural network is what you give as input. So for doing that, if you're going to use a binary system, okay, that's zeros and ones, you have to have a binary, produce a binary representation of the information you want to classify. Mm-hmm. So imagine that your input is a pair of real values, okay? Well, we could give the bit directly the bits of the representation you are using for that real value to the wizard. But that, in fact, is a not very good input for the wizard. The wizard is very good at processing images. So you have to prepare an image for that value inputs to there. One way to deal with that is to produce, for instance, a thermometer, a histogram representation of that value. So you imagine a scale from 0 to, for instance, 31 bits, 0 to 31, and have 32 bits. And use that scale, you scale these real values in that range and produce that thermometer value of the inputs. Well, why you do that? Because look, if I use imagine that was an integer instead of floating point. Mm-hmm. 7 is a value very near to 8, but the patterns are a complement. They are very, very different. So the image is very. So that's the tricky points about using wizard. Mm-hmm. And in fact, this makes lots of difference on the response. I think I could, if you allow me, I could share. Let me see if I have it here. Hold on. Okay. I think we have a little bit of time, is it?
I think we can go all the way to 11 a.m. So
to 11 a.m., 1 hour and a half. Okay.
Yeah, I think that's it, which is actually good because I have more questions. Of course, we can end it earlier, but I think we can go all the way to 11 if we must.
Okay, so let me. Hold on. It's the other way. The other one. Sorry, guys. I'm looking for a notebook here where. Oh yes, this one is nice. I will stop sharing this, okay? And I will. Let me try to. Where are you?
Oh, sorry. We can go all the way to 10:30. That's when the break starts.
Oh, okay.
I just checked it again at the website.
All right. Let me find me. Here is my. Okay. Let me separate this this window. Okay. Here. All right. Let me go back. Okay, so I will share again another window.
Okay.
Window. This one is okay. Is it there? Okay.
Yes, I can see it.
All right. So in this notebook, you have this. This is input data. You have two classes, right?
You can see.
And hold on. Let me run this. Okay, run anyway. It has it. It's taking a bit long. Let's see. Uh-oh. I have to. I think. Oh,
I think you had to run the previous cells first. Yeah.
Oh, Jesus Christ.
Yeah, I always get lost in these collab cells as well.
Oh gosh. Come on. Oh my God, it's not.
That was something else I was going to comment. I was going to ask if there's any open implementation of Wizard. And I was very glad to know about the last slide, in the last slide, that you actually have a PIP package. That's very cool.
That's it.
I'm definitely going to use it with my students as well.
Just look for it. It's okay. Hold on. I think. Oh. Did I miss something? No. Huh? Oh, that's the thermometer encoding. Okay.
Okay, that's what you mentioned.
Yeah. I can pass this this collab as well for you.
Oh, it has an arbitrary resolution as well.
Yeah. Okay, you can see the example here. And we have also this, we call the circular thermometer, is when you want to always give the half bits in one, half bits in zero.
Interesting. So this is already implemented in the library package.
Yeah.
Oh, that's very cool. That's nice.
I will be happy if everybody start using and developing weightless models. We have many opportunities to do that.
Awesome. I have another question.
Go on until you get there.
Because as I can see, it seems that it's, the patterns are very sensitive to the positioning of objects. And did you ever think of extending W and N's to scale invariant and rotation invariant features as well? Maybe using convolutions or something like that?
Yeah, that in the beginning, some time ago, we did that using the mental images. We did the neocognitron wizard. Neocognitron was the earlier version of the deep neural networks based on the visual system, our neuron, the real neuron visual system, without lots of layers and lots of convolutions. And yes, we are doing it again now, but we had this in I think 12 years ago we have this, but let me, and yes, it is, but I have recent results on accelerating deep neural networks. Let me hold on, because I don't know if is it okay already? Yeah, this is the data.
Okay.
And
oh, now it ran. Yeah.
Let's see. Oh, here I have the tuple size and the resolution, and I will run it here. Okay. And you have two encodings, the thermometer encoding and the circular encoding, I think. Is it working or not? Oh, yes, it's here. Oh, that's the representation. Look at the circular one. That's not well appropriated to this case because you start to get this noise on the borders, okay? And look, the data is not homogeneous. So look what happens. You have this, kind of very precise and odd border, but you cannot say that it's not generalizing because, yeah, you want to see that linear, that very regular line there, but it's not really there. You are imagining that.
Yeah, the decision function is similar to the ones that we find in decision trees. It's very interesting. Which brings me to my last question that I saved for you. What are the possible causes of overfitting in WNN? When you expand too much the number of RAM units, maybe? Are there any possible, traps that you can avoid to avoid overfitting of these models?
Well, overfitting is...
or to increase generalization, mostly?
Yeah, but it depends on the generalization. The size of any tuples that you use is directly related to the generalization you want from the system. If you give a very low address, you generalize a lot. If you give a very big address, the contents will be very sparse. That goes to the specialization, goes the other way.
Yes,
so
makes sense.
The input size is defined by what stuff are you presenting there. That's why you have this in the collab. You can see you have I have this resolution, how many points I'm going to treat, and what will be the end. So you can do any combination of that. And normally, as Wizard is very quick, you just look for the best architecture and run it again instead of doing all the training in other models. You spend time looking for the best architecture because this is very quick. You can explore many architectures very quick.
And it's also very easy to translate to hardware because it's a bunch of lookup tables if you think about it.
Sure.
But also, when you increase the size of the data, you probably increase the size of the lookup tables as well, and also decrease the generalization, right?
You could keep the same. You could keep
the
same.
Because it's not all these samples. Yeah.
You can just add more RAMs to the system, or you can reduce the number of RAMs and with bigger RAM. That's a compromise. We have enough.
The size of the RAM units is also trainable, right? You can use like 3 samples, 4 samples to address. I think.
Well, that depends on the mapping you are doing for the RAM.
Cool.
Okay.
Very interesting. Okay, so since we don't have any more questions, Felipe, do you have any final words? Otherwise, I would like to thank you once again for this very interesting talk. I think we should talk more because I'm always looking for hardware-friendly network models. So definitely your research is very interesting to what I'm doing right now. Thank you once again. Very enlightening.
No, thank you, Mateus, for the nice handling of the talk. And we have also it's not very far. We have an FPGA implementation of Wizard. And it uses hash functions to implement RAM, so you can work with any size of the n tuple logically. Okay.
That's very interesting to hear.
But we're still working on this, including Mauricio Bertenitz and also now Lizzie John from Texas, Austin, Texas. Also, I think she's a kind of famous, and we are working now on this using Weightless in microarchitectures in general. We want to go in applications that goes into circuits now, and that if you got interested, get in touch. We could work together. Okay.
Definitely. Thank you very much, Felipe. I would like to thank you once again then. And since we don't have any more questions, I'll see you all in the next session. We have a short break now, everyone. And at 10:45, we're going to have a talk with Mr. E.B. Friedman on distributed on-chip power delivery for heterogeneous nanoscale integrated systems. Thank you once again, Alexandra.
Thanks, Professor Mateus, for presenting the section. Many thanks to Professor Felipe França for your valuable presentation.